There we go. Turning the sound back on. Probably a good idea. Right. Welcome back. I still have my Christmas Santa hat on. My Nim Santa hat. On from the ending of the last stream. Yeah, so today is going to be a quick one. I don't have a lot of time. So possibly we'll only have time for day 1 today. But we'll see how far we can get. Thanks. Right. So Advent of Code day 12. Again, haven't done 9 and 10 yet, but we'll skip ahead to day 12. We did day 11 yesterday. Had a pleasantly surprising a surprisingly easy day part 2, because we were clever about part 1. So hopefully that will be the case today as well. Then I might be able to get both of them, but we'll see. Day 12. Hot springs. Oh, we're getting to the hot springs. Since I haven't seen day 9 and 10, I'm not sure if this is an actual hot spring or if they are like warm springs. No idea. But I guess we'll find out today. You finally reach the hot springs, or hot springs. You can see steam rising from secluded areas attached to the primary ornate building. Okay, so probably hot springs. As you turn to enter, the researcher... Ooh, this links to day 11. Right, yeah, we met a researcher on day 11, and he needed some help. The researcher stops you. Wait, I thought you were looking for the hot springs, weren't you? You indicate that this definitely looks like hot springs to you. Oh, sorry, common mistake. This is actually the onsen. What? Onsen are hot springs. Right. So a Japanese thing. Probably butchering the pronunciation of this word then. Someone with a suspicious Norwegian name seems to have joined the chat. The hot springs are next door. You look in the direction the researcher is pointing and suddenly notice the massive metal helixes towering overhead. This way. Right, so they were hot springs, not hot springs. It only takes you a few more steps to reach the main gate of the massive fenced-off area containing the springs. You go through the gate and into a small administrative building. Hello! What brings you to the hot springs today? Sorry, they're not very hot right now. We're having a lava shortage at the moment. So we're going somewhere to get lava, I guess. You ask about the missing machine parts for Desert Island. Oh, Olive Gear Island. Oh, wait. We're onto a new island. I didn't realize. So we're on Gear Island. Interesting. Olive Gear Island is currently offline. Nothing is being manufactured at the moment. Not until we get more lava to heat our forges. And our springs. The springs aren't very springy unless they're hot. Say, could you go up and see why the lava stopped flowing? The springs are too cold for normal operation, but we should be able to find one spring enough to launch you up there. So they're gonna just bounce me on a spring up to another island? There's just one problem. Many of the springs have fallen into disrepair, so they're not actually sure which springs would even be safe to use. Worse yet, their condition records of which springs are damaged, which is my puzzle input, are also damaged. you'll need to help them repair the damaged records. In the giant field just outside, the springs are arranged into rows. For each row, the condition records show every spring and whether it is operational or damaged. So similar inputs or similar things, symbols to yesterday. This is the part of the condition records that is itself damaged. For some springs, it is simply unknown, so question mark, whether the spring is operational or damaged. However, the engineer that produced the condition records also duplicated some of this information in a different format. After the list of springs for a given row, the size of each contiguous group of damaged springs is listed in the order those groups appear in the row. So 113, it's a contiguous section of one spring, 3 springs. Makes sense? This list always accounts for every damaged spring, and each number is the entire size of its contiguous group. That is, groups are always separated by at least one operational spring, so this would always be 4, never 2, 2. That makes sense. So, condition records with no unknown spring conditions might look like this. However, the condition records are partially damaged. Some of the spring's conditions are actually unknown. For example, so here we can see we need a one spring section here. Then we need another one spring, but this has to be ending this one. So this one can start anew. And then we have the 3-1 there. Here again, we're looking for a 1-1-3 situation. So this has to be 1, this has to be 1, or this and this for that matter. And then these 3 have to be all damaged. This one, a bit trickier. We can't just say that this one is damaged because this one is. So this one has to be good. This one has to be good for this to be a 1. These 3 have to be damaged for this to be a 3. Then this can't be damaged. This is damaged. So this can't be damaged. And these have to be all damaged. Interesting. Equipped with this information, it is your job to figure out how many different arrangements of operational and broken springs fit the given criteria in each row. In the first line, there is exactly one way separate groups of 1, 1, and 3 broken springs in that order can appear in that row. The first 3 unknown springs must be broken, then operational, then broken, making the whole row like this. The second line is more interesting. This could be a total of 4 different arrangements. This one always has to be broken to satisfy the final contiguous group of 3 broken springs. And each double question mark must hide exactly one of the 2 broken springs. Either question mark could be both broken springs, or they would form a single contiguous group of 2. If that were true, the number afterwards would have been 2, 3 instead. Since each question mark can be either pound dot or dot pound, there are 4 possible arrangements of springs. The last line is actually consistent with 10 different arrangements. Because the first number is 3, the first and second star must both be blah, 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 blah. Or not star. The first and second question mark must both be dot. If either were pound, the first number would have to be 4, blah, blah, blah. However, the remaining run of unknown spring conditions have many different ways they can hold groups of 2 and 1 broken springs. So these are all the possibilities for this to be satisfied by this input. In this example, the number of possible arrangements for each row is like this: 1 arrangement, 4 arrangements, 1 arrangement, 1 arrangement, 4, and 10 arrangements. Adding all of the possible arrangement counts together produces a total of 21 arrangements. For each row, count all of the different arrangements of operational and broken springs that meet the given criteria. What is the sum of those counts? Right. Interesting, interesting. Bit trickier than I might have expected, but I think we can get through this pretty easily. At least part one. The solution I have in mind might not be fast enough for part two. Depends a bit on what they throw at us. So basically, my idea is to grab these unknown sections and then try first write a group parser that will spit out 113 for this, 113 for this, 1316 for this. So first write that parser, then collect these, try all the different possibilities and see if we get these arrangements, and then spit out the total amount. It should be fast enough for day one. So let us actually first start with this so that we can make sure that our group algorithm is correct. So count groups takes a string as input, returns a sequence of integers. What it does, I think we're just gonna do an import of string utils. We're gonna say x.split on dots, and then we are going to map it. So we need secutils as well, and do it.length. So basically this splits the thing up on dots. So it will split these into dots. It will also split these empty ones. So yeah. But if we run this for line in lines in our sample input, echo out the line with its groups counted. Trying to go so fast I mistype. Right, so 1, 1, and then 9. Right, because we have to first split on the space that separates these, and we have to grab the first part of that input. That was the 113 for the first one, which is correct, but this one has a bunch of zeros in it, which is obviously not correct. That is from the dots, contiguous dots that don't match anything else. So what we're gonna do, we're gonna filter it and say it is not equals to 0. Now it should filter out all of the ones where this predicate is false. So that should give us only the ones that are true. So 113, and let us actually do, let's do this, and we're gonna say, give me split 0 count groups, compare that to the truth, which is in here. That is looking good. So now we have our count groups. Now we can do our next input, this test input there with the question marks in it. Let us quickly, before we do that though, create a get count groups, I guess. Oops. Takes a string, which returns another sequence of integers. And what we're going to do here, we're just going to do x split on comma and do a map it on parse int. So that's going to give us that is going to parse out the sort of the true result in the same format. So as you can see here, it turned this string into a sequence of numbers, the same sort of the same data type. So now we can do if we do this and just verify that these are equal, they are now the same type, so we can compare them properly, and that runs without error, so that's good. So now we need to run through this. We need to gather up all the question marks, and we need to try every single possibility. So these have two possibilities, damaged or not damaged. So what we could do is set up sort of an n bits number, and then like count up until we are at this size of bits. Or we could do sort of a more county way, say that, well, we have two possibilities. That means we have 2 to the power of 3 ways of organizing them. Wait, that's not quite right though. Well, yeah, that should be fine. But why do we have 8? I thought that would be 9. So 0, 0, 0, that's 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, yeah, so that's right. Those are all the possibilities of 3 bits. Of course, it would be 8. Did I mention I'm tired today? So, if we now do this, we will of course have some weird results. Well, we get an error. It's not really a weird result. If you go back to our echoing scenario here, we can see that we now have some bad inputs, because of course this isn't able to properly count things. So we now need to we need to count all the characters, all the question mark characters in our first thing here. So I guess there should be a count function. Yes, we have a count, takes a string and a character. So we can say split 0.count and count all of the question mark characters. So this should give us 3 for the first one, 5, 8 for, those are hopefully all good. We're going to bring in the math module so that we can do power. And of course we want to do 2 because we have 2 possibilities to the power of this count. So those are the possibilities. The power function works with floats for some reason. Well, it doesn't have an int overload for some reason. So yeah, here we can see 832, 256. Of course, we know that these are going to be integer in size, so we can do this. Right. guess we could also do shift this left by split 0.count and then do a -1. I think that should be the same. Oh, we need something to actually count. Again, I'm tired, so I might have messed that up. Okay, not the -1. So yeah, there you can see all of the different numbers. Now, interesting part here is that if we take this number, so for I in this number, if we decrement that by 1 and go all the way down to 0 and write this out as a binary number, that requires a size. Just give me 8 bits of binary. Where did that output go? Say what now? Did it mess up that range somehow? Oh, count up versus count down in them. You can't do reverse loops without invoking the countdown iterator. ... only does count up. Yeah, we can see here now that we have in these last 3 bits, we can see that we have 0, 0, 0, 0, 0, 1, all the way up to our 1, 1, 1, which is, if you remember from my typing on the side here, the 8 possible patterns. So what we can now do is that we can replace all of those 3 sort of counts with these bits, right? So we can now, if we do let unknown, so just the amount of unknowns, is equal to this. We actually don't need those. And now we can say all the way up to, but not including unknown. There we go. Yeah, that looks good. So now we know that we need to grab the 3 lowest bits. The easiest way to do that is to grab the lowest, then shift right once, the next one, shift right once. So what we can do here, we don't have the positions, so this is going to be a bit expensive, but we are going to create a var out of split 0. So store that as a what could we call it? We could call it corrected split 0. Of course, it's not corrected yet, but we are going to correct it. And then for n in 0 all the way up to, but not including the unknown, as a number, it grew quite a bit more than I had. Unknown is of course already to the power of, which I didn't intend. I intended to do this like that. Yeah, we're not using corrected, I know. Right. So here for our first one, we should now see, let me just break after the first iteration through the loop, just to make this easier to see. So yeah, for this one, 0, 1, 2, 0, 1, 2, 0, 1, 2. That's good. Does that 3 times. We don't actually care about this number because what we're going to do is we're going to say corrected dot replace, and we're going to replace a question mark with if I, we're going to store, we're going to do that, if n and ob1, so that the lowest bit is equal to 0, then we're going to do a damage character. Otherwise, we're going to do a find character. Well, let's do that the other way. Just seems more sensible. Now it should be a dot. And we are going to, so the replace function has, replace. The replace function has, this one, sub, places every of oh wait, I thought this took a max count. Because we don't want to replace every occurrence. We only want to replace the first occurrence. Well, no matter, we can use the find. So we can do corrected dot find this one. We know how many there are, so we don't need to make sure that we actually find something. This will just return an index. We are going to set that to one of these two characters. And for each loop, of course, we have to shift this right by 1. So what this does is that it takes this bit mask and it checks, is this one a 1 or a 0? If it's a 1, I'm gonna put a damage there. If not, I'm gonna put a good there. So in this case, put a damage there, then shift the entire bit pattern right, so it's now 1 0. Check the 0. Do the same thing. Shift 1 over. Now we're checking this one. And if we now look at our corrected down here, oh, actually, we have to grab our corrected. Wait, we're doing something wrong here. Oh, I wasn't thinking about this error. I know what that is. It's just the operator precedence rules in them. So basically now we're only checking one. Right, we're doing all of our patterns at once, which is not what we want to do. We want to do this. And just don't write these out. Clean this up a bit. There we go. Clean this up a bit as well. Oops. So now, after this loop, we have our corrected string. If we run this, we will see that these are all the possibilities where we have replaced all of these 3 first ones with actual characters, which is what we want. And now we want to only count the patterns that are good. So we do a sum up here, sum 0, and then we say up here we store the truth, the actual count groups, and then we check down here if corrected dot count groups is equals to the truth, then add 1 to the sum, and if we remove this one, we can echo out our sum. I I do it for every loop just so that we can check that stuff looks good. So in this case, only one matched for the first one. There's exactly one way. So yeah, one arrangement for the first one, 4 for the next, so our sum should be 5. That's good. Then 1 for the next, yes. And 7, yeah, so 1 for this one. 7 plus 4 is 11, so we get to 11, and then 10 for the last one. Looking good. Grab my puzzle input. Of course, a bit more complicated, and our solution wouldn't be... Oh crap, that was day 11. I wrote this... Oh, I didn't write out that file. I thought I had written out the file, so I overwrote it. Not to worry, we can always go in here and say nope. Isn't it cached? Oh, just restore. Yeah, cached is for there we go. So now that file is back, but that's not actually what we are here for. We want to get to run this on our actual input. Just do this out there. Run our code. Ooh, that was even slower than I expected it to be. How long is this? Okay, it's a couple of lines. And we are doing quite a bit of work here. I guess we should, since this is taking so long, let's do a release build. That should speed it up considerably. And let's do some comments in the meantime. There we go. So no time for comments. Nim isn't that slow when you just compile with the right flags. That's the right answer. You're 1 gold star closer to restoring snow operations. Come on. If part 2 is easy, we'll be able to get this one as well. But probably not. As you look out at the field of springs, you feel like there are way more springs than the condition records list. When you examine the records, you discover that they were actually folded up this whole time. To unfold the records, on each row replace the list of spring conditions with 5 copies of itself, separated by a question mark, and replace the list of contiguous groups of damaged springs with 5 copies of itself, separated by a comma. So this row would become this row. The first line of the above example would become this monstrosity. In the above example, after unfolding, the number of possible arrangements for some rows is now much larger. So this is one arrangement. This has 16,384 arrangements. 2,500 and 500,000 arrangements. So definitely not something we can do with my silly way of doing it. This would be way too slow. For this, our entire answer was lower than one of these, and you saw how long it took. So I think I will have to call it the day here, because I simply don't have time today to keep going. I think so. To do this, just trying to think of a good way of doing this. I think we were on the right track, but we are working on strings. We are running find for once, which is not going to be the fastest. We could pre-index the finds. We can store the result of find and then start looking from a specific index. Find supports that. But I think we would benefit from going to a not a string format, going to something a bit smarter, like memory wise. That might not even be enough. I mean, these are in groups, so I guess we could verify group by group. Could be a thing that we could do. So we can see, like, we can solve this for as many groups as possible. So this one is able to solve 1, 1. And then this contiguous group here is able to solve 3, of course. And it can solve 3, 1. And it can solve 3, 1, 1. But it can't solve any more. So that eats this part of the list. Then this eats this part of the list. So on and so forth. I think that would be a way of doing it that could be faster. Instead of trying every single possibility. Basically just pruning out some of the things that we know won't work. But yeah, might have a look into that on my next stream. I don't think I will have time to stream tomorrow, unfortunately. But maybe the day after. So we have one comment here. Haha, today I learned a nim 1 bit is called OB1. Yeah. I think the 0b prefix is quite common. Oh, you also didn't find a workable approach. Well, now you have my take on it. Maybe we could do it the string way by splitting these out into, like, splitting on dots, finding groups, and eating from this input. That could maybe work. But I think this case, well, it's only 1 arrangement, so it would be just as slow as our first one, I guess. Oh no, it wouldn't. It would have a lot more. Yeah, I'm not sure. I'm not sure. Basically, there has to be some kind of optimization that we can do. Something that just prunes off a lot of the options, because now we are testing every single option. So for each line, we're going through each unknown or each possibility. And of course, this is a kind of a slow way, I guess, of replacing these. And of course, splitting and map it and filter it. These are slow operations. So just optimizing would give us something. But yeah. That's all I had time for. Someone says, do you want a hint? I'm not sure I do. Because I simply don't have time right now to solve this. So I might come back later and have a look at it. Right. Of the generated bit numbers, you could prune the non-fitting count question mark before replacing. Non-fitting count. Well, it wouldn't be a non-fitting count because it's generated from the count that we have. Anyways, as I said, I have to run. Have a good Advent. Have a good time playing with Nim if you're doing Advent of Code in Nim this year. And have a good time doing it in any other language if you just enjoy watching these streams but don't enjoy using Nim. Yep, that's it from me today. So